On the morning of January 5, 1943, four Japanese Aichi D-3A dive bombers, call sign VAL, emerged from the clouds over Guadalcanal. They dove toward a U.S. Navy task force operating in the waters off Cape Hunter. One bomber scored a direct hit on the New Zealand cruiser Achilles before the group broke off their attack. As the VALs banked away, anti-aircraft gunners aboard the USS Helena almost casually fired a few salvos at the departing aircraft. Lieutenant Red Cochran, commanding Helena's aft 5-inch battery, watched as two shells screamed toward the distant bomber. They didn't need to hit it. At 70 feet from the target, both shells exploded without making contact. The VAL disintegrated in midair, raining debris into the ocean below. It was the first combat kill by a weapon that military officials had feared using, that British commanders had doubted, and that had cost over $1 billion 1940s to develop. Inside those shells was a device so secret that its very existence was classified at the same level as the Manhattan Project. So revolutionary that General George Patton would later write, "The new shell with the funny fuse is devastating. I think that when all armies get this shell, we will have to devise some new method of warfare." It was called the proximity fuse, and this is the story of how skepticism, secrecy, and stubbornness nearly prevented the Allies from deploying the weapon that would change warfare forever. To understand why the proximity fuse was revolutionary, you need to understand just how bad anti-aircraft fire was in 1940. When World War II began, shooting down a fast-moving aircraft was almost impossible. Gunners had two options, and both were terrible. The first option was the contact fuse, a shell that exploded only when it directly hit something. Against a maneuvering aircraft traveling at 300 miles per hour, the odds of a direct hit were astronomically low. It was like trying to hit a flying bird with a thrown rock. Possible, but not practical. The second option was the timed fuse, a clockwork mechanism set manually before firing. A crew member would calculate where the enemy plane would be in a few seconds, set a timer, load the shell, and fire. If the calculations were perfect and the timing was exact, the shell would explode near the target. If either was slightly off, the shell would detonate harmlessly in empty sky or sail past the aircraft and explode on the ground below. The statistics were horrifying. At the start of the London Blitz in 1940, British estimates suggested it took 20,000 anti-aircraft rounds to shoot down a single German bomber. Other estimates put the figure as high as 100,000 rounds per kill. Some said it was as low as 2,500. Nobody knew for sure, but everyone agreed anti-aircraft fire was essentially throwing up a wall of steel and hoping the enemy flew into it. The tragedy wasn't just wasted ammunition. On December 7, 1941, when Japanese aircraft attacked Pearl Harbor, American anti-aircraft crews fired frantically at the incoming bombers. Of the 48 civilian casualties that day, most weren't killed by Japanese bombs. They were killed by improperly fused American anti-aircraft shells that exploded when they hit the ground in Honolulu, rather than in the air near their targets. The problem wasn't just ineffective, it was deadly to the very people it was meant to protect. What the military needed was impossible, a shell that could detect when it was close to a target and detonate automatically. Scientists and inventors had been proposing proximity fuses since the 1930s. Patents existed in multiple countries, but everyone agreed it couldn't be done. The technical challenges were insurmountable. In June 1940, as France fell to German forces, President Franklin D. Roosevelt approved the creation of the National Defense Research Committee, the NDRC. Its chairman was Vannevar Bush, an MIT-educated electrical engineer who would later oversee the Manhattan Project. The NDRC's mission was simple: solve the military's unsolvable problems by bringing together the best scientific minds in America. That same summer, Rear Admiral H.G. Bowen approached the NDRC with a problem that kept naval commanders awake at night. The U.S. Navy's surface ships were sitting ducks for air attack. In the Pacific, where the Japanese had demonstrated devastating air power, American carriers and battleships needed better protection. The Navy needed a proximity fuse that could work in a 5-inch anti-aircraft shell, their primary long-range defensive weapon. The NDRC assigned the project to Section T of the Department of Terrestrial Magnetism at the Carnegie Institution in Washington. Leading the effort was Dr. Merle Tuve, a brilliant physicist who immediately understood the magnitude of the challenge. The theory was simple enough: create a miniature radio transmitter receiver inside the nose of a shell. It would send out radio waves, which would reflect back from any nearby object. When the reflection reached a certain strength, indicating the shell was close to the target, the fuse would detonate. Simple in theory, impossible in practice. Consider what had to happen. The fuse would be fired from a gun, experiencing an instantaneous acceleration of 20,000 Gs, 20,000 times the force of gravity. That's like going from 0 to 2,800 feet per second in milliseconds. The shell would then spin at 25,000 revolutions per minute as it traveled through rifled gun barrels, creating enormous centrifugal force. Inside this violent environment, miniature vacuum tubes, as fragile as Christmas ornaments, had to survive and function. The radio transmitter had to work. The receiver had to detect faint reflections. The amplifier had to trigger the detonator. And all of this had to happen in fractions of a second, powered by a tiny battery using electronics that in 1940 filled entire rooms. Oh, and the whole device had to fit in the nose of a 5-inch shell, weigh less than 5 pounds, and cost less than $20 to manufacture. Section T's solution was ingenious. They used the shell's metal body as the antenna. They developed ultra-miniature vacuum tubes, modified from hearing aid technology, that could somehow survive the shock of firing. They created a circuit that would detect the Doppler shift in reflected radio waves, the same principle that makes an approaching train whistle sound higher-pitched. When the radio waves bouncing back from the target reached a certain frequency, indicating proximity, a thyrotron tube would act as a switch, releasing energy from a capacitor to fire the detonator. But making it work in a laboratory was one thing, making it work in combat was another, and making it work while keeping it absolutely secret was yet another challenge entirely. While Section T worked frantically in Washington, British scientists had their own proximity fuse program. They had been working on the problem since 1939, focusing primarily on photoelectric fuses, devices that used light-sensitive receptors to detect nearby objects. Prime Minister Winston Churchill himself was pushing for rapid development, calling the effort part of Britain's Wizard War against Germany. In late August 1940, a British scientific mission led by Sir Henry Tizard arrived in the United States. The mission's purpose was to share intelligence and technology between the Allies. Professor John Cockcroft, a member of the mission, carried details of British proximity fuse research to Washington. On September 17th, he briefed Captain Wilfred Gillette at the Naval Research Laboratory. 2 days later, he met with Dr. Tuve. Tuve was excited by the British progress, but skeptical of their approach. The photoelectric fuses had serious limitations. They could be triggered by reflections from clouds or the ocean, and they were useless at night. The British radio fuse work was promising, but far from operational. Tuve believed the American approach, using a combined oscillator detector circuit and ruggedized vacuum tubes, was the path forward. The British, for their part, viewed the American device as unproven technology. It was the classic "not invented here" syndrome. British engineers had been working on the problem longer. They had more combat experience. They had actual data from the Blitz. And here were the Americans, late to the war, claiming they could solve a problem that Britain's best scientists had struggled with for years. But the real source of doubt wasn't technical, it was tactical. Military officials on both sides were terrified that a dud fuse might fall into enemy hands. If the Germans or Japanese captured an intact proximity fuse, they could reverse engineer it and develop countermeasures, or worse, build their own. The device was so secret that Pentagon officials initially refused to allow its use over land under any circumstances. It could only be used over open ocean, where a dud shell would sink and couldn't be recovered. This paranoia reached absurd levels. Even when the fuses began proving their effectiveness in the Pacific, British commanders refused to use them over England. It didn't matter that London was being pounded by German bombers. It didn't matter that thousands of civilians were dying. The risk of compromise was too great. The fuses sat in warehouses while people died. While military officials debated whether to use the proximity fuse, American industry was performing a manufacturing miracle. By early August 1942, the USS Cleveland test-fired the first prototype fuses in the Chesapeake Bay. The tests were a complete success. Now came the hard part, mass production. Each proximity fuse contained approximately 130 miniaturized electronic components. Every component had to meet exacting specifications. A single defective vacuum tube, a loose wire, a bit of moisture, any of these could cause the fuse to fail, or worse, to detonate prematurely and kill the gun crew. The fuses had to work in tropical heat and Arctic cold, in rain and salt spray, after being stored in ammunition magazines for months. 5 companies were selected for production: Western Electric, Raytheon, Sylvania Electric Products, Eastman Kodak, and the Crosley Corporation in Cincinnati. Crosley alone would eventually employ 10,000 workers, operating around the clock, 7 days a week, producing 16,500 fuses per day. By the end of the war, Crosley had manufactured over 5.2 million fuses, 24% of the total 22 million produced. The workers, mostly women, assembled the delicate components by hand. It was tedious, eye-straining work. They weren't told what they were building. Security was so tight at the Sylvania plant in Ipswich, Massachusetts, that women were searched when entering and leaving, weren't allowed to bring purses, and even the local police and fire departments couldn't enter the building. Some women worked as couriers, traveling between plants with armed guards, carrying blueprints they weren't allowed to read. The entire program cost over $1 billion in 1940s dollars, equivalent to roughly $15 billion today. It was one of the most expensive weapons programs of the war, rivaling the Manhattan Project in scale. All for a device that weighed 5 pounds and fit in the palm of your hand. And for 2 years, military officials were too afraid to use it. The breakthrough came not through official channels, but through desperation. In November 1942, the Navy sent 5,000 proximity fuses to Pearl Harbor. Of those, 4,500 were distributed to Pacific Fleet vessels. The restriction remained: use only over open water, never over land. On January 5, 1943, USS Helena made history with that first kill off Guadalcanal. But it was what happened next that proved the fuse's worth. Throughout 1943, as Japanese forces launched desperate air attacks across the Pacific, the proximity fuse transformed naval anti-aircraft defense. The statistics were staggering. In 1943, naval guns fired 36,370 anti-aircraft rounds. Only 25% used proximity fuses. The rest were conventional, timed, or contact fuses. But those 25% of proximity-fused rounds accounted for 51% of all aircraft kills. The improvement was dramatic. Where traditional fuses required 1,000 rounds per kill, proximity fuses needed only about 250 rounds, a four-fold improvement. The lethal fragment area told the story even clearer. A conventional timed fuse, if it detonated at exactly the right moment, could damage anything within about 60 square feet. A proximity fuse, detecting the target and detonating at the optimal distance, had an effective lethal area of 3,000 square feet, 50 times larger. Near misses became kills. One Section T scientist later calculated that proximity fuses destroyed 278 enemy aircraft that would have required perhaps 46 kills with conventional fuses. A Navy study found night-kill ratios increased by 370%. Japanese pilots who had grown accustomed to American anti-aircraft fire that they could evade with hard turns suddenly found themselves flying into death zones where evasion was impossible. The impact went beyond statistics. Some naval historians believe the proximity fuse forced a change in Japanese tactics. When conventional approaches became suicide, Japanese commanders turned to kamikaze attacks. If you're going to die anyway, take the enemy with you. Vannevar Bush, who oversaw the entire OSRD during the war, credited the proximity fuse with a seven-fold increase in the effectiveness of anti-aircraft artillery. It may have made the difference between victory and defeat in the Pacific. While the Pacific War proved the fuse's effectiveness, Europe remained off-limits. That changed in June 1944 when Germany unleashed a new terror weapon on London. The V-1 flying bomb, nicknamed the Buzz Bomb for the distinctive sound of its pulse jet engine, was Hitler's attempt to break British morale through automated terror. From the first day of attacks to the end of August 1944, Germany launched 9,300 V-1s at England, an average of 120 per day. Each V-1 carried a ton of high explosives. They flew fast enough to outrun most fighters and low enough to complicate interception. When the Germans adjusted the V-1s to fly as low as 1,200 feet, British defenses struggled. Winston Churchill, who had been pushing for photoelectric fuses in 1940 and had remained skeptical of the American radio fuse, now personally intervened. Despite the prohibition on land use, despite the fear of German capture, Churchill authorized the deployment of proximity-fused anti-aircraft shells along England's southern coast. American physicists at the Applied Physics Laboratory quickly modified the fuses for the British 3.7-inch and 90mm guns. The devices were rushed into production at the Crosley factory in Cincinnati. Churchill then authorized a special flight of Lancaster bombers to transport the fuses across the Atlantic. Such was the urgency. The impact was immediate and dramatic. By the end of the fourth week of V-1 attacks, anti-aircraft batteries equipped with proximity fuses were destroying 79% of all incoming rockets. The defense of London had been transformed overnight. One British artillery officer described the difference. Before proximity fuses, they threw up a wall of fire and hoped. After proximity fuses, they hit what they aimed at. From the first day to the end of August, proximity fuses accounted for thousands of V-1 kills. As one Section T scientist wrote in a letter, "Actually, you can be sure that the VTF has saved the lives of thousands here." The skepticism had finally been overcome. On December 16, 1944, Germany launched its last desperate gamble, a massive offensive through the Ardennes forest that would become known as the Battle of the Bulge. 3 German armies smashed into American lines, driving deep into Belgium. It was Hitler's attempt to split the Allied forces, capture the vital port of Antwerp, and force a negotiated peace. That morning, Colonel George Axelson, commander of the U.S. 406th Artillery Group, faced an impossible decision. German forces were overwhelming the 38th Cavalry Squadron near Monschau. They needed artillery support urgently. Axelson had just been issued a new type of ammunition, proximity-fused artillery shells, but General Eisenhower had not yet authorized their use over land. The ban was still officially in effect. Axelson made the call. The emergency trumped restrictions. His gunners loaded the proximity fuses and opened fire. The effect on German troops was unlike anything they had experienced. Traditional artillery was survivable if you were dug in or behind cover. The shells exploded on impact with the ground, and the blast and shrapnel traveled outward and upward. If you were in a foxhole or behind a wall, you had a good chance. Proximity-fused shells exploded 20 to 30 feet above the ground before hitting anything. The blast and shrapnel rained straight down. There was no cover, no protection. Foxholes became death traps. One German prisoner later described the attacks as quick, powerful bursts for which there was simply no defense. Another said the explosions seemed to come from everywhere at once.
3 days after Axelson broke the embargo, General Dwight D. Eisenhower formally requested authorization for unrestricted use of proximity fuses. On December 21st, 5 days into the offensive, all restrictions were lifted. 200,000 proximity-fused shells were rushed to the front. What happened next shocked even the American commanders who deployed them. General George Patton's Third Army, racing north to relieve the besieged town of Bastogne, encountered German units trying to cross the Sauer River near Echternach. American artillery batteries, now equipped with proximity fuses, opened fire. The shells exploded over German infantry as they raced across a wooden bridge, paddled rubber boats, and swam the icy river. Some soldiers broke and ran back into the town. Others froze in terror. Patton later wrote to the War Department, "The new shell with the funny fuse is devastating. We caught a German battalion which was trying to get across the Sauer River with a battalion concentration and killed by actual count 702. I think that when all armies get this shell, we will have to devise some new method of warfare. I am glad that you all thought of it first." The psychological impact was as significant as the physical casualties. German troops, who had felt safe from timed artillery fire because bad weather prevented accurate observation, suddenly found themselves exposed. The effectiveness of proximity fuses exploding over their heads caused what some reports described as a minor mutiny, German soldiers refusing orders to leave their bunkers during an artillery barrage. Throughout the Battle of the Bulge, Allied anti-aircraft artillery using proximity fuses destroyed 417 German aircraft. Artillery using proximity fuses decimated German formations caught in the open. Towns like Malmedy were saved when American artillery broke up German attacks with air-bursting shells. By January, when the Allies counterattacked and pushed the Germans back, Patton was telling everyone who would listen, "The funny fuse won the Battle of the Bulge for us." So how did this magic actually work? The Mark 53 fuse, the most common version used in 5-inch naval guns, was a marvel of miniaturization. At its heart was a tiny radio transmitter operating at roughly 180 to 220 megahertz. The transmitter used the metal shell body as an antenna, with a small electrode cap on the nose to control the radiation pattern. As the shell flew toward its target, the transmitter continuously emitted radio waves. These waves radiated forward in a cone-shaped pattern, deliberately focused to be most sensitive perpendicular to the shell's flight path, where enemy aircraft were most likely to be, and least sensitive along the axis of flight. This directional sensitivity was crucial because it prevented the fuse from triggering on the reflection from the ground until the shell was very close. The reflected radio waves were picked up by a receiver circuit and amplified by miniature vacuum tubes. Here's where it gets clever.
As the shell approached the target, the frequency of the reflected signal would change due to the Doppler effect, the same phenomenon that makes a train whistle sound higher-pitched as it approaches you. The fuse's circuit was designed to detect this frequency shift. When the reflected signal reached a specific frequency, indicating the shell was within about 70 feet of the target, the amplified signal triggered a thyrotron tube, which acted as an electronic switch. The thyrotron released energy stored in a tiny capacitor, which fired an electric detonator. This detonator then triggered the main explosive charge in the shell. All of this happened in a few milliseconds. The genius was in the engineering details. The vacuum tubes, developed in collaboration with Western Electric and Raytheon, were reinforced with special mounting systems that could survive the 20,000 G acceleration. The circuits were potted in compound to resist moisture and vibration. Safety systems prevented premature detonation. The fuse wouldn't arm until after firing, when centrifugal force from the shell's spin closed a mechanical switch. A self-destruct feature ensured that if the fuse didn't detect a target, it would explode after a set time, preventing duds from falling into enemy hands. Everything was miniaturized to an almost absurd degree. The entire radio transmitter-receiver system, including power supply, amplifier, and detonator, fit inside a space smaller than a coffee cup, and it had to work every single time because lives depended on it.
Despite its widespread use in the final year of the war, the proximity fuse remained one of the best-kept secrets of World War II. The Germans never figured it out. Captured German intelligence documents show they were working on their own proximity fuse designs, perhaps as many as 50 different approaches, but none ever entered service. Their efforts were hampered by Hitler's 1941 order to halt development, resource shortages, and the lack of rugged vacuum tube technology. When the Germans captured unexploded proximity-fused shells, and they did occasionally, they were baffled. Some German scientists theorized the fuses used radio detection, but couldn't believe the miniaturization was possible. Others thought they were detecting ground proximity through barometric pressure or some other mechanism. The truth that each shell contained a functional radio transmitter-receiver set seemed too advanced to be real. The Japanese made even less progress. They didn't develop a working proximity fuse until the final months of the war, and it saw virtually no use. Post-war interrogations revealed that neither Axis power ever understood the full scope of Allied proximity fuse deployment. They blamed their aircraft losses on pilot error, on overwhelming numbers, on bad luck, never on the fact that American shells could think. After the war, the secrecy continued. The proximity fuse technology was immediately classified and remained restricted for years. The Soviet Union, desperate to obtain the technology, succeeded through espionage. Julius Rosenberg, the Soviet spy who would later be executed for passing atomic secrets, had earlier stolen a working model of an American proximity fuse while working for a defense contractor in the mid-1940s. Fortunately for the United States, the model he obtained was for a different application, not the highly valuable anti-aircraft version. When the war ended, military analysts began calculating the proximity fuse's impact. Vannevar Bush estimated it increased the effectiveness of anti-aircraft artillery by 7 times. Navy studies showed it reduced the ammunition required per kill by 75%. Army assessments credited it with saving Antwerp and breaking the Battle of the Bulge. Winston Churchill called it one of the weapons that proved potent in defending England. General Eisenhower, in his memoirs, was even more emphatic. It seemed likely that if the Germans had succeeded in perfecting and using these new weapons 6 months earlier than they did, our invasion of Europe would have proven exceedingly difficult, perhaps impossible. He was referring to German superweapons like the V1 and V2, but the proximity fuse was the Allied counter that made those weapons survivable.
The cost, over $1 billion in 1940s dollars, $15 billion in today's money, was enormous. But consider the alternative. Without the proximity fuse, how many more ships would have been sunk? How many more aircraft would have gotten through? How many more V-1s would have hit London? How much longer would the Battle of the Bulge have lasted? The investment was microscopic compared to the lives saved and the strategic advantage gained. The technological legacy was equally profound. The proximity fuse represented one of the first smart weapons, a munition that could sense its environment and make a decision. The principles developed for the VT fuse would later be applied to guided missiles, from the Nike anti-aircraft missiles of the 1950s to the Patriot missiles used in the Gulf War, to modern air-to-air weapons like the Phoenix and AMRAAM missiles. Perhaps most importantly, the proximity fuse demonstrated what could be achieved when scientific research, industrial production, and military necessity aligned. Section T, at its peak, employed an estimated 3% of all physicists in the United States. The manufacturing effort involved over 100 factories. The security apparatus kept the secret through millions of rounds fired in combat. It was an organizational achievement as significant as the technical one. So why were military officials so reluctant to use the proximity fuse? Why did British commanders doubt American innovation? Why did it take 2 years of successful testing before the Pentagon allowed unrestricted deployment? The answer reveals something fundamental about military organizations and technological change. First, there was the legitimate security concern. The proximity fuse was so revolutionary that losing the secret to the enemy could have been catastrophic. But this fear became paranoia, leading to absurd restrictions that cost lives. The weapons sat in warehouses while cities burned and soldiers died, because officials were more afraid of what might happen than concerned with what was happening. Second, there was institutional skepticism toward unproven technology. The British had been working on proximity fuses longer than the Americans. When Section T claimed to have solved the problem, British engineers dismissed it as American overconfidence. Even within the U.S. military there were doubters, commanders who had trained their entire careers with timed and contact fuses couldn't believe that a better solution was possible. Third, there was the not invented here syndrome. British scientists had their photoelectric fuses and their radio research. American scientists had different approaches. Each side was convinced their method was superior, even when evidence suggested otherwise. It took Churchill's personal intervention to overcome British reluctance, and even then some officers remained skeptical. But the doubters were wrong. Every single objection, that it couldn't be miniaturized, that the tubes couldn't survive firing, that mass production was impossible, that the cost was too high, that the security risk was too great, every objection was overcome by the determination of Section T scientists, the skill of American manufacturers, and the courage of commanders willing to take risks. When Lieutenant Red Cochrane fired those first combat rounds off Guadalcanal on January 5, 1943, he proved that near misses could become kills. When Winston Churchill authorized deployment over England in 1944, he proved that the security concerns, while real, were outweighed by the lives that could be saved. When Colonel Axelson broke the land use ban at the Battle of the Bulge, he proved that sometimes you need to trust your weapons more than your fears.
The proximity fuse never received the public attention of the atomic bomb or radar. Most people have never heard of Section T or Dr. Hurrell Tuve. The women who assembled millions of fuses by hand in Ipswich and Cincinnati returned to their lives after the war, never speaking of what they had done, bound by secrecy oaths they kept for decades. But the impact was undeniable. General Patton called it devastating and credited it with winning the Battle of the Bulge. Admiral King called it essential to fleet defense in the Pacific.
Eisenhower said it made the difference between victory and defeat. Churchill said it saved London from the V1 onslaught. These weren't exaggerations. The statistics backed up every claim. From 20,000 rounds per aircraft kill down to 250 rounds per kill. From 60 square feet of lethal area to 3,000 square feet. From 417 German aircraft destroyed at the Battle of the Bulge to 79% of V1s shot down over England. From hundreds of thousands of casualties prevented in the Pacific to the German soldiers who refused to leave their bunkers. The numbers told a story of transformation. Today, you can see a cutaway Mark 53 proximity fuse at the Smithsonian National Air and Space Museum. The miniature vacuum tubes are still visible, the circuits still intact. It looks impossibly delicate, and it is. That something so fragile could survive being fired from a gun, could function in combat, could change the course of battles, seems almost magical even now. But it wasn't magic. It was physics and engineering. It was determination and ingenuity. It was thousands of people working in secret toward a common goal. It was women assembling components they didn't understand for a purpose they weren't told. It was physicists solving problems that everyone said were unsolvable. It was commanders willing to trust innovation over tradition. The proximity fuse succeeded because people refused to accept that the problem was impossible. Section T refused to believe that vacuum tubes couldn't be ruggedized. American industry refused to believe that mass production couldn't be achieved. Naval commanders refused to believe that near misses couldn't become kills. And eventually, even the doubters, the Pentagon officials who restricted its use, the British engineers who dismissed it as unproven, the commanders who feared enemy capture more than friendly casualties, even they came to realize the truth. Sometimes the weapons that change wars aren't the biggest bombs or the fastest planes. Sometimes they're 5-pound devices that fit in your hand. Sometimes they're ideas that people say are impossible, pursued by scientists who don't accept that answer, manufactured by workers who never know what they're building, and deployed by commanders brave enough to break the rules when lives are on the line. The funny fuse, as Patton called it, proved that innovation triumphs over skepticism, that security concerns, while important, must be balanced against strategic necessity, that the gap between laboratory and battlefield can be bridged with determination and industrial might, and that sometimes the most devastating weapons are the ones that turn near misses into direct hits. By the time the war ended in 1945, over 22 million proximity fuses had been manufactured. They had been fired from ships in the Pacific, from anti-aircraft batteries defending London, from artillery pieces in the snow of the Ardennes. Each one represented a technological triumph. Each one proved the doubters wrong, and collectively they helped win a war. The proximity fuse wasn't just a weapon. It was proof that when necessity drives innovation, when scientists and engineers and workers and soldiers all pull in the same direction, the impossible becomes possible. The skeptics doubted, the bureaucrats restricted, the enemy never believed. But in the end, the funny fuse had the last laugh, one explosion at a time, 70 feet from targets that never saw it coming.